Okay, so it should be recording now. So we started talking before, but I didn't introduce myself. So I'm Rehab, and I'm going to be taking you guys through the optimization strategies workshop today. And so a little brief outline of what we're going to be going through is we're going to be building off of the previous workshop where you got to get introduced to Keras and how to build a neural network. And so we're going to use kind of the same network and the same data set, except today we're going to be talking about how do we set different hyperparameters like epochs, batch sizes, learning rates, and other things so that we can better optimize our network. And so we will get right into it. The first step is just to import the libraries. Yeah, that was perfect, quick. And so I'm assuming that people are going to be going through with me, but if not, if I'm going too fast, too slow, just let me know. And then the next thing is to download the data set. So this is the Pima Indians diabetes CSV. So just go to this link and click right here to download it. As you can see, I've already downloaded it. You can see it at the bottom here. So I'm not going to download it again, but this is how you would do it. And then we just come back, and then over here you click files, and then just drag and drop it right here. And again, as you can see, I got a little ahead of myself and already did that. But you just, once you insert it here, you can run the read CSV function just to make sure that you can read it. And so that's step one, get the data set. And so now this is all going to be kind of repetition from the previous workshop, is actually just splitting the data into 20% training data, 80% testing data, and kind of dropping our target column, all of those things. So I'm not going to focus on them because this is just exactly from the previous workshop, but it's something that you got to do every single time. And so we are doing a 20-80 split here. So 20% test, 80% training data. And we're going to be normalizing the data using the transform function. And then finally, this is where we get to the good stuff. So now we're going to start building our network. And right here, this cell, we're going to be coming back to it and running it a lot of times throughout the workshop. I think the idea is every single time we're going to be changing a parameter, we want to come back and rebuild this network because we don't want the network kind of to change a hyperparameter like the epoch value and then test it out without rebuilding it, because then it's going to be biased because it's already been trained. So we're going to be doing a lot of scrolling back here. So then what we will do is, once we've built this, and then this is going to be a very simple one. So what we have is we have just kind of an input layer, and this is our output layer, which is just a value of 0, 1 for do they have diabetes or not. And we have a hidden layer here, a hidden dense layer, and it's going to be, we're going to have this global variable here, which is going to keep it constant throughout so that we can also later keep using this tensor board, which is going to be really useful for us. And so I'm going to set up this tensor board, and all you really have to do now is just run this. Later on, we are going to be looking at graphs to kind of see how small versus big epoch sizes matter, things like that. But once you run this, you should see a new folder right here called logs. If you see it, that's great. And if you don't, let me know. So let's start with, I'll just skip this one for now. Let's start with determining optimal hyperparameters. And so there are several hyperparameters that are going to be really useful when you're building a neural network. For today's workshop, in terms of kind of hyperparameters, we're going to be looking at epochs, batch size, and learning rate. And we'll look a little bit also at optimizers when we look at learning rate. But the idea is we want to kind of see if we get a value that's really small or a value that's really big, how is that going to affect our accuracy, our ability to get optimal results, things like that. And how do we actually find a perfect value? That's a really good question. And so let's start with epochs. And so just to give a really brief recap, epochs are essentially the number of times that the learning algorithm, in this case, we're going to be using the Atom optimizer, and this is our learning algorithm overall, how many times it goes through the entire data set. So with an epoch size of 10, we're going to go through the entire data set 10 times, or 300 times over here, or 100 times for the third one. And so theoretically, if you go through the data set too little times, you might be underfitting or risk of not finding optimal results. If you go over it too many times, you might be overfitting, and kind of also then you're not getting optimal results. And so what we want to do now is just run the cell with epoch equals 10, because now we've set it to 10, and skip these two for now because these are for later. And then we want to actually fit our model. So we run this and we let it run. Right now it's gonna be really fast because there's only 10 epochs, as we can see. So right now the accuracy is actually kind of low, which I guess is expected with a pretty low epoch value of only 10. But let's actually go back and see over here in our, lost my thought, right here in the tensor board. This is where we're going to keep scrolling back up to see. So figures. The funny thing is you prepare and you prepare, and then something goes wrong when it's the real deal. No problem. Okay, looks like I just had to reset this. Maybe give it a minute. Okay. Looks like we're starting to see something. So I have way too many things clicked. So all I care about is the most recent runs. For you should probably only see two because I ran this a bit before just in preparation. But let's click these little buttons to make sure everything fits. And let's see over here. Okay, so what does this graph actually tell us? And so for starters, it's telling us that, for example, the epoch loss, if we remember back to when we're calculating our loss, what are we actually doing? And we're trying to find local or ideally global minima in our kind of curves that we're looking for so that we can minimize our loss function. In this case, our loss, we see that it's decreasing and decreasing and decreasing, but it never actually reached a plateau. So what this is telling me is there's room for it to decrease more. We might actually be able to get way lower of a loss if we keep going. So this is telling me 10 epochs is not nearly enough because it hasn't plateaued. We want to see a plateau. And so maybe if we increase the epoch size to say 300, something will change. And so let's actually go ahead and try that. Let's try epoch size 300 and see how that impacts this graph, see what happens. And so first things first, like I said, every time that we want to change the hyperparameter, we're going to want to come and rebuild this network because at this point we've already trained it with 10 epochs. I don't want it to be trained at all so that I can kind of get a fresh start. So run this one more time. Scroll down to the epochs, and now I want to run epoch equals 300. So now we've reset the epoch value. This one's going to take definitely a longer time to run. And so let's fit the model and let's let it run. So something to consider is with really high epoch values, they are going to take a longer time to run. So that's definitely a con in terms of computation. So we always want to find a value that's low enough that it gives us our optimal results, or high enough that it gives us our optimal results, but not kind of too low that it's underfitting, too high that it's overfitting or starting to diverge. Here, we're Goldilocks in this case. We're trying to find the value that's just right. That's our goal. So it looks like it is done. Perfect. There's going to be a lot of kind of running things in this in this workshop. And so as you can see in this tab over here, I added a tab of AI jokes just in case we're running something and it takes too long. We'll switch tabs. We'll get a good laugh. Okay. So we have trained our model with 300 epochs. So now let's go back up to our tensor board. And now what I'm going to do is up here, you can see this refresh. Let's just refresh it. Okay, now we see all these lines. So I do not want the ones with the 10 anymore, the 10 epochs. I just want the 300. So let's click this to fit it and click this little button to fit it so the graph is perfect. So we can see that our accuracy compared to before has definitely, I guess right now it's not showing, but it's definitely improved a lot. But if we look at our loss, so it looks like over here, our loss is decreasing. Perfect, that's what we want to see. But then at around 100, our training and validation losses start to diverge, and that's not what we want. That's telling us that once we're starting to diverge, maybe we've gone too far and we don't want to see that. And so we can see now how when we had an epoch size of like 10, all we got was this little top part. It was just decreasing. And we're like, okay, we want to see a plateau. But when we had an epoch size of 300, now we're at the point where we are just increasing kind of and starting to diverge away from each other, the training and validation sets. And that's also not something we want to see. So both are non-ideal in this case. And so now let's look. And from my site of view, or kind of my point of view, it looks like at around 100 is when it starts to plateau, but right before these two lines start to diverge. And so let's see at 100. If we set our epoch size to 100, what are we going to be seeing? What are we going to be looking at? And so again, repetition is key here. I think that's going to be great. So we're going to go ahead and rebuild our network just so we get a fresh palette. And then we scroll down to this little epoch section. Now I'm going to run epoch equals 10 so that now we've set epoch equals 10. And then over here, this is our model.fit. So this is the same thing that kind of you've been using from even last class, where we're giving our training data a batch size, which we'll talk about later. And this is the key here. This is where this epoch value, we're setting it here to 100, here to 300, here to 10. So now I've set it to 100, this value right here. And so let's fit the data. And this shouldn't take too long, but it definitely will take less time than the 300. Yeah, so there's a question, we're looking at the plateauing of the validation curve and not the training curve, right? So you are looking for a plateauing of the validation curve, I agree. Usually what that entails is also plateauing of the training curve, because I don't think it's likely that we're going to get the actual validation curve to plateau if your training didn't plateau. So it's going to be almost a match. But yes, we're looking for the validation curve to plateau and the training curve, if that answers your question. And of course, Sarah can chime in whenever if you want to add something. So yes, I got a thumbs up. Good. Perfect. So what did we just do? We just ran we set epoch to 100 and we fit the model. And so here, if we scroll down, it looks like it completed running. So let me just scroll down all the way here. It's always easier to look at the graphs in here, but just kind of to look at this value. If you remember back to when our epoch size was 10, our accuracy was like 0.64 or 0.65. And so our accuracy increased by 10%. It's still not perfect. There's definitely things that we can do to improve it. And we'll talk about those things when we talk about other hyperparameters. But I mean, increasing your accuracy by 10% just by looking for an optimal epoch value shows you how powerful it is to get the proper epoch value. Another question, why couldn't the software come up with the correct number of epochs? So the software, the way that at least Keras works is it's a template or a skeleton for you to fit in all the numbers that you want. Because the fact is that usually, depending on if you are doing a really simple data set or something super complicated, this one I would argue maybe more on the simpler side, a little complex, but not that much, then your epoch values are going to change drastically depending on what your data looks like and things like that. And so the software, just the way it works is that you set it yourself. That being so, it doesn't really set it for you. That being said, there's a lot of research that actually goes into finding optimal hyperparameters. From my experience, a lot of it is trial and error. So it's going to be like, you have to try something that's too small, try something that's too big, and then try something that's a little bit too small, but not perfectly like big enough. And you just keep trying and trying until something works. And that's why we want a validation set. But yeah, it's not a satisfying answer to your question. The fact that software doesn't choose it for you, and there's a lot of trial and error. But that's, I guess, where computer science is at this point. Does that answer your question? Okay, perfect. So let's see. So yes, we just ran the 100 epoch, and like I said, we talked about how it went up over 10% from 10 epochs just by looking for a better epoch value. And now let's come back here to the tensor board and refresh. And as usual, I will scroll down here. Every time you run it, it's going to add more training and validation logs here. And so I'm going to unclick the one before because all I want to see now is the thing that I just ran. And then I'm going to click this button to fit the lines into the graph so that we get a better view. And oops, did I close this? And now let's see. So this looks a lot better than what we saw before. What we see now is, number one, our epoch accuracy continues to increase until kind of the validation set is near 0.75, the training is near 80% or 0.8. And it's just starting to plateau, which is good. And the same thing with the loss, except of course here we're minimizing, not maximizing. And it's going down and it just starts to plateau, but it hasn't diverged too much yet. You could definitely argue that you could even use a little bit of a lower epoch value if you want to, because it might be diverging a little bit here, maybe 90. But it really is a matter of trial and error. You just want to try things until something is ideal for you or you're getting optimal results, your validation set is looking better. And once that happens, you end up with a big smile on your face. So that's epochs, kind of looking at epoch values and how minimizing the epoch value, maximizing it, or getting something that is just right is going to affect these curves. Now we're going to move on to the next section, which was about batch sizes. We're going to do a similar type of thing where we're going to look at like a small one, a big one, and then a medium one, and then look at the same graphs and see how the different batch values impact the graphs. Does anyone have any questions about epochs before I move on? While I wait for questions, I'm going to close these logs just because they're taking up a lot of space that I feel might be wasteful. Perfect. And so what we'll do again is refresh our network. So we have now started with a clean slate again. And then let's go down to our second parameter, hyperparameter, which is batch size. And so now let's start with a really small batch size of 2. And so do you guys remember what a batch size is? It's essentially when you have a data set, you want to with batch size, you're splitting up your data set into little subsets of that batch size. So in the case of 2, you're going to have lots of sets of 2 kind of values. In the case of 200, you're going to have lots of sets of 200 sets. And batch size is going to really depend on how big your data is. If you only have 100 data points or rows in your data set, there's no way you can have a batch size of 200 because you don't even have that much data. But if you have a batch size or a data set size of like 10 million data points, then a batch size of 200 is going to be too small. You might want even like 1,000 at that point because you have millions of data points. And so these numbers are just specific to the data set that we have, how many columns or rows we have, but it's definitely going to change based on the size of the data that you have. So healthcare data, I think usually they are dealing with millions of data points. And so your batch size might be really big at that point. But relative to the set, it's not too big. So I ran batch equals 2. This is the same thing that we saw before with epochs, except for now I set epochs equal 100 since we determined that's kind of the best one that we've seen. And then here batch is now just going to be equal to this variable batch. And we are setting what batch this batch is equal to over here. So I've set it equal to 2. And now I'm running it. So it's actually quite fast, which is nice. We're halfway there. Some of these jokes are inappropriate, so I'm glad they cover them up. I'm looking for one that would be funny. You guys have any jokes in mind? Okay, we're done. We'll come back to this. I want to get through at least one joke today. I think it's a reasonable goal in life. So, batch size of 2 gave us a accuracy of 0.74. Okay, not amazing, not bad. And let's go up and see our sensor board. So let's refresh. And then let's unclick the previous run. And then let's fit this. And so with a batch size of 2, what does that mean? It means we're splitting the data set into subsets of 2 values. And so for a really big data set of like some thousands, for every 2 values, we're updating the weights in our neural network. That's a lot of computation, and that's kind of a lot of subsets that we're going to have for a big data set. And so what we see here is our loss is kind of, because we're doing so many computations throughout, our loss is starting to diverge, which is, if you remember back to epochs, that's when we had too many epochs. And so we could have 2 solutions to this problem if we want to get to a point where we're just starting to plateau, but we haven't started to diverge. And one solution is we could actually just reduce the epoch size. If you want to have a really small batch size, have a smaller epoch size. So maybe in this case, an epoch size of around 40 would be good. Similarly, we could keep the epoch size and increase the batch size. And so let's try that. Since we've already played around with epoch sizes, let's try to increase the batch size to 200 and see what happens. And so I was almost going to forget there, but we want to rebuild our network. And then we go down here, and now we're going to reset this variable batch to 200, and that's pretty large for our data set. And then we fit it. So theoretically, this should be a lot faster because we're doing a lot less computations because we're kind of grouping 200 points together. And for every 200 points, we're only going to update the weights once at the end of going through those 200. Whereas before, after every 2 points, we were updating the weights. So that finished pretty fast, except our accuracy is 10% lower than what it was at a batch size of 2. So now we're like 10% lower at 64. So let's scroll up and refresh our TensorBoard. That is not what I want to see, but let's unclick this and make this fit. Yeah, so what am I looking at? These shapes look weird. And so I'm going to focus on the epoch loss because I think there's a lot we can see from this graph, which is, okay, we started at some high loss. We're trying to minimize our loss because we don't want to lose. And then we start to decrease, but we haven't plateaued. We still have a lot of potential to decrease. And so before, when our batch size was 2, we decreased all the way, we plateaued, and then we diverged. Here, with an epoch size of 200, we're not doing enough computations to actually progress and minimize our loss the way that we want. And so that's not ideal. And what we're ending up with is we haven't even plateaued, let alone had the opportunity to diverge. And so that lets us know that, okay, maybe 2 is too small of a batch size. 200 is too big. So what's an ideal batch size? 2 and 200 are very far apart. So it could be 40, it could be 50, it could be 20. The next one we have to try is 20. I happen to think that 20 is a good one, but I've had a few kind of opportunities to actually run it myself and do trial and error. Try 40, try 50, try 20, and then 20 looked good. But if you're just starting out with 2 and 200, maybe then try 100 and see how that works, kind of the middle ground. And then if 100 is it's starting to diverge, try something even lower than 100. And so I don't think I reset this. Let's set our batch equal to 20. And then let's fit the model. And so it's running. This one's very fast. Like we're already at 100 epochs. Okay, and I don't know if it's just me, but this is the highest accuracy we've seen yet. Because when we had an epoch size of 2, we were at like 74%, 0.74. And with epoch size 200, we were about 0.64. And now we're at 0.76. So improvement, I think that's good. Let's go to the TensorBoard and refresh. Okay, so I want to unclick the previous run and I want to fit the graphs onto this table, or the points onto this graph. So this is looking better. I like what I'm looking at here. What I'm seeing with the loss is they're just starting to plateau. Yes, they're starting to diverge a bit, but I think we can live with that because for the validation, which is the orange line, it has just started to plateau, which is good. And similarly here, there's a little bit of noise for sure in the accuracy, but it looks like it's starting to go up and it is starting to kind of plateau at the top, which is nice. At around here, we see value 0.76, or I should be looking at the orange 77. Those are good numbers to be looking at compared to before. And so that is the idea behind looking for an ideal batch size. And it's very similar to looking for an ideal epoch size. Like we did the same procedure. We ran our network, we built the network, we set an epoch value or we set a batch size value, and then we fit the model and looked at the accuracy and the loss. And then we went from there, are we diverging? Are we even plateauing? Are we not plateauing? Asking those questions and then determining whether we need to increase or decrease our hyperparameter to reach better results. So now that we've gone through epochs and batch sizes, we can start looking at learning rate. I am going to first reset our network. Of course, if there's any questions about anything or something's not clear, feel free to ask. Okay. So I'm going to close this. And let's look here at optimizers and learning rate. So when it comes to, if you were to actually write your own code for a neural network, this would be difficult to change because then you're looking at completely different algorithms, like the Atom optimizer is the one that we've been using throughout. We can try the SGD optimizer, which is stochastic gradient descent, and see what happens there. And there's many other ones as well. But with Keras, the great thing is all you have to do to change your optimizer or even the learning rate, which we're going to do over here, is a single line of code. And so this is why this is so great, because it makes things really simple in terms of our job isn't to actually worry about the itty bitty details of how the code works, but to determine what hyperparameters we want. And so our goal is just, what does learning rate mean? How do I find the optimal learning rate? And then setting it to that learning rate is going to be all we want to do. And so I won't run this one because this is the same kind of one with Atom that we've been running throughout. But let's try this new optimizer for stochastic gradient descent. And if you remember from the lecture, stochastic gradient descent is essentially the algorithm where we have a gradient and we're trying to minimize our weights so that we get kind of minimal loss and maximal accuracy and balancing that. So there is a question in the chat. Do you generally do this in this order, epoch to learning rate? Does changing one affect the optimal setting of the other? Yes, changing one does affect the other. And so that's why if we remember back to when we were looking at, I think it was, if I just remember, I don't remember which ones there were. Yeah, maybe this one. But if we remember back to when we were, for example, talking about epoch and batch size, when we had a batch size that was super small, and so actually maybe that was this one. Yes, here we go. We had a batch, this one was when we had a batch size of 2. And so we saw that our plateau started to diverge. And so a way to solve a small batch size could be to just increase the batch size, but you could also just decrease the epoch size. And so here you could see how different hyperparameters can fix the same problem. And so yes, changing one does affect the other, because before we had determined that 100 is the perfect epoch size, but once we changed the batch size, everything was like, oh no, now I'm confused. Now 100 is too many epochs, and that's because our batch was too small. Same thing for learning rate. If you have a learning rate that's really, really small, so you're learning very slowly, then it could be okay if you have a really high epoch size so that you can go through the data so many times and learn. If you have a learning rate that's really, really big, I don't know if there's a way to solve that, because then it's a little problematic because you're just jumping around and you're not going to be finding your local or global minima. But for sure, if your epoch or if your learning rate is really small, the way to solve that maybe is just to have a lot of epoch sizes, or you could just increase learning rate a little bit. So that was the long answer. The short answer is yes, changing one parameter does affect how the others are. it's kind of a set. You have to make sure everything works together. Yep. And like Sarah said, that's another reason why the computer doesn't know how to calculate the correct epoch size, because there's so many parameters that are going to affect it. Cool. So I don't remember if I had rebuilt this, but just in case I'll do it again. And let's go back to the optimizers and learning rates. So we said, let's try the stochastic gradient descent. So we're trying to kind of minimize our weights. And the default learning rate is 0.001. That's the one that we've been using throughout. Like when you played with different epoch sizes, with different batch sizes, we were using a learning rate of 0.001. And let's try to change that and see what happens. And so here we have the same code that we had before. We're going to set our batch size to 20, since we determined that's a pretty good number. We're going to set our epoch size to 100, since the two of these seem to match together. And over here, we have our optimizer. Before, our optimizer was set to atom. Here, another way to do it is to just like create a variable, call it optimizer, whatever you want. And then we're going to be using that variable here. And then use the variable that, or the optimizer that you want. And inside it, you can set the learning rate. So here we've set it to 0.05. But before we get ahead of ourselves, I'm going to make it 0.5 because, spoiler, that's a very high learning rate. And let's see what happens. So I'm going to run this. And let's see what happens. So the accuracy is actually looking okay. Let's scroll down. So yeah, the accuracy is pretty good. Let's see the TensorBoard. So I want to unclick the previous run. Oh, I should refresh it to get the most recent run. Perfect. And so it's fitting. What is going on here, and why is there so much noise? Like before, we were getting lines that looked pretty nice. Like we saw a little bit of up and down before, but this is a lot more jumping up and down, and that's not ideal. It's telling us that our algorithm is kind of just going all over the place and like estimating or predicting different values. Our accuracy is obviously not consistent. If 1 second it's 0.74, then the next second it's 0.775, and that's within kind of 5 epochs. And so all this jumping around is because with such a high learning rate, what's happening is our kind of weights or our accuracy, it's just bouncing around, and it's not able to take the time to actually consistently learn something and stick with it, because it's always kind of saying, okay, I have to learn really fast, so let me just try everything, rather than when you take your time and you do it right. So it's a life lesson and a computer science lesson. Take your time when you learn things, and at the end you'll achieve a high accuracy. So yes, and like Sarah said, every batch is impacting the model way too much, and so we're seeing it fly around way too much. And similarly here, like we're still seeing that it's plateauing, but it's just bouncing around, and that's not what we want to see. So let's reduce that learning rate. We had 0.5. Let's try something like, oh, I don't know, 0.05 and see what happens. But before I do that, let me reset my network. Perfect. So let's change this to 0.05 and compile the model and fit it. So it looks like it is done. That was quite fast. Perfect. And we're consistently seeing this 0.7662 accuracy. Interesting. But yeah, let's go back up to the tensor board and refresh. Whoa. So I'll just keep these together for just a second before I get rid of the old run. But do you see how much less noise there is in the pink line versus the red line or the lighter blue line? Like, there's been quite a bit of improvement in terms of consistency, which is good to see. You don't want to see all that noise. And similarly here, it's a little bit hard to see just because the colors are very similar, but I will remove the older ones and then we can see what these look like. There's definitely still a little bit of noise here, but there's only so much we can do. But we can see that kind of that plateau is much cleaner. It did start to diverge though, so maybe that's telling us that our learning rate is too small, or maybe we need less epochs. So there's lots of things to consider here if you want to kind of decrease the epoch size or maybe even decrease the learning rate even more. Let's try to make it even smaller just one more time. And then we can move on to the next one. But this is just kind of playing around with it to make sure that we really understand how we're impacting the accuracy and the loss. And so I've just reset the network. And now I'm going to rerun the model with a learning rate of 0.005. We're just adding and removing zeros at this point. So now it's a little bit slower, but I think it's done. Ooh, the accuracy went down. Interesting. Did it go down? Yes, it was 7.6 before. Now it's 6.8. So it did go down quite a bit. So let's go back up and refresh. Okay, so we can't see everything to get, oh, we do see it. Okay, so one thing before I kind of get rid of the old one is we can see how for the lower learning rate, our loss is much higher. So that's actually not something that we want. And our accuracy is much lower. Before it was like 7.6 or 0.76, now it's like 0.68. Also not something we want. So I guess in that case, we learned that maybe we thought we needed a lower learning rate, but in fact, 0.05 is better. So you learn by kind of going too low, too high. And I like this. I won't dwell on it too much because I think we've gone through this idea a few times. And so now let us rebuild this network and scroll back down. And so at this point, we have completed all of the hyperparameters that we wanted to talk about. So we talked about epochs, we talked about batch size, and we just talked about learning rates. So I'm going to close this to save some space. And this is just a little summary for you guys to read. The gist of what it says here is just that, as unsatisfying as it may seem, adjusting hyperparameters and finding optimal ones is something that comes with experience and with reading papers about people who have done full kind of research projects on finding the perfect epoch value or trial and error, things like that. Because there's a lot that goes into it. There's definitely researchers that spend a lot of time and energy trying to figure out what's the best optimizer to use in certain situations. What's the best epoch value or batch size to use in this case versus that case, and how does that impact the accuracy? So yeah, you will learn definitely from experience and trial and error. And that summarizes the bigger section of this workshop. So now what's left is to talk about regularization. And that is essentially all that's left. And then at the end, we have a little playground. I didn't know what else to call it, section for you guys to kind of play with your own optimizers, batch sizes, epochs, things like that. So let's talk about regularization. So regularization is really easy to fix or to implement in Keras, and it's really useful for preventing overfitting. And so let's think about how we can do that. And so over here we have two methods for you to implement regularization. The thing that I should say beforehand is because this data set is kind of simple, we have like a few columns and we're predicting whether or not diabetes exists. When you implement the regularizer, we're not actually going to see a very drastic difference, like a 10% accuracy difference, but do not let that fool you. Regularizing is quite important, especially as your project or data set gets more complex, and the risk of overfitting is something that's like you're not really sure if you're overfitting or not, and the risk increases. Then you definitely want to know how to do it and implement it. But over here, we might not see very big of a difference. And so let's first, let me just rebuild that. I've built it so many times, I'm not sure if I've already done that. But alas, yes, just one click, no problem. Okay, so what do we have here? We have, first, we have a link for you to read more if you want. Second, we have a quick question in the chat, so let me read that. So the accuracy in the example we used here ranged at best at around 0.75. Yes. An AUC of around 0.75 would be considered okay, not that great in clinical field. I agree. So I was wondering if that's what you usually get here, or it's a function of the database we used for our example. Yes, so you're completely right. We have been getting accuracies that are not ideal, especially for clinical environment where you really want to make sure that your accuracy is high. I would attribute the lower accuracy to a few things. Number one, definitely the data set. Number two, it could be that there's more things that we could do. Maybe if we add more layers, which is something we'll talk briefly about at the end of the workshop. But adding more layers, looking more into kind of how to optimize different factors and the data set itself are going to be things to consider. One other thing that's really important is the size of the data set. The more data you have to train, the better your predictions are going to be. So if your data set is only 100 points and we split it up 80% for training, 20% for testing, sure, like it's 80-20 split, that's great. But that means you only have 80 cases to predict 20 cases from. And what if those 80 cases are not properly representing all the cases that exist? And so part of the problem is probably our data set is not too big enough. But I agree, if you're ever going to be like predicting something for healthcare, you definitely want to work on these strategies to make sure your accuracy is increased. Yeah, and then Sarah was saying that AUC scores tend to be higher than accuracy, so an accuracy of 0.75 might actually be competitive for many scenarios, which is another great point. So yeah, maximize your data and use lots of these tips. They're going to be valid all the time, kind of looking at epoch values, batch sizes, learning rates, regularizing. These are all going to be useful things to do in the future if you're working on a project. So what are we looking at here? We are looking at the same model that we built before. So if we go all the way to the top, we had a model, we kind of had the sequential function, we had an input, function, and then we had a, what's it called? Dense layer. But now we're going to be building a completely new model, and we've called it R model. Stands for regularized model. And so let's see what we have to do. And so adding regularization to a cross network is actually quite simple. All you have to do is add this kernel regularizer equals L2, and we set it to 0.01. So you kind of learned about L1 and L2 in lecture, and so that's good. One thing that you don't really have to worry about because it's already in the code, but if you do this on your own, it'll be useful, is that to use the L2 function at the top, we had to import L2 right here from regularizers. So sometimes you'll run something and it won't work. You might just need the import statement for it. And so let's go back. Okay, so let's look here. We have our regularizer, a regularized model. And it looks like it has, we've created it, which is good. And this is exactly the same as the model we had previously, except with this kernel regularizer in all of the hidden layers. And so let's fit the model and see how it looks. And so we're starting off with a, okay, it's increasing a bit. Some of these values are looking pretty good. Okay, 7662. It seems, although we keep coming back to this number. Yeah, so there was just a message from Sarah in the chat. Quick definition of regularization is that it's the addition to the loss that penalizes the model for being too complex. And so if our model is too complex, that means that we risk we risk overfitting. And so by adding a regularizer, it's almost oversimplistic, but I like to think of it as we're trying to make this complex thing more regular. Maybe that's where the name actually came from. And so making it more regular means it's less complex, means we aren't overfitting as much. And so now that we have run this, let us actually first look at the accuracy, which was nice. Next, what I want to do is I want to actually connect this to the caress. Oh, it's already here. Okay. So what I want to do is copy this. And I think that if I refresh this, it should show. I have too many things showing here. Okay. So this is what we had before. It looks like our accuracy is improved. Oh, I think because before we were looking at a super low learning rate, but it's not as perfect as this. Yeah, so let's actually compare when we had done a lower learning rate or 0.05 learning rate versus this one, because this one's doing a 0.001 learning rate by default, I believe. So it's something to think about. But it looks like it's doing okay, but it's not ideal for sure, although the accuracy looks pretty good. And it's a little bit noisy, but that's definitely something that's important, because maybe the reason that our accuracy was so or higher before is because we might have been overfitting a bit. So just things to consider. It might be the case that sometimes you're getting an accuracy of 100%, but that's because your model is like, it's a polynomial and it's just turning in all the right direction so that it hits every point, but it doesn't actually make sense. You'd be better off with a linear model or something. And so regularizing fixes problems like that, if that makes sense, hopefully. But regardless, let us go and try something else with regularizers. And this is another method of implementing regularization. And instead of actually adding this kernel regularizer, we could add this dropout layer, which is going to randomly drop data points from our network or data set so that it kind of prevents complexity at the same time. And so what I'm going to do, and yes, drops weights to 0. What I'm going to do is I'm going to comment the line we had before with the kernel regularizer. And then I'm going to uncomment the layer without the regularizer with the dropout layer. And so let's do that. Okay. Perfect. I think that is good. Now let's do the same thing. Let's just run it. And now let us train it with a batch size of 20, an epoch size of 100. Yeah. Ooh, I saw 78% somewhere. Okay, so I think this is the best accuracy we've seen yet, which is always good. Because before we were at like 7.6, now we're at 7.7. Improvement is gradual, but it exists. So now that we have seen this, let's go back up to our tensor board and refresh it. Okay. Looks a little messy, so let's unclick the previous run and fit the board. So yeah, we're seeing the same type of thing. Our training data is a little bit noisy, but for our loss, it looks like our validation set is a lot cleaner in terms of little jumps. But regardless, this is an improvement, I would argue, using the dropout layers. And that's another way to do the same thing where we're regularizing our model or our network. And it's pretty effective, it seems. It looks like, yeah, it just started to plateau and it looks like it didn't actually start to diverge, which is nice. So let's scroll back down. Let's see what we have here, because we've reached the end of this section on regularization. Although I do want to just touch on a few things that we couldn't really include in this workshop just because we had to kind of work on time and things, but I think that it could be useful. So for example, over here, and this is just little things that are nice to know. Let's look at where we actually create our batch, our network. Okay, right here. Right here we have a place where we set our optimizer, and we already talked about how you can change this. We tried changing it to the SGD or stochastic gradient descent. Metrics, we're looking at accuracy, and something to consider is our loss. Right now we're looking at binary cross entropy, which is, I believe, just looking at if your prediction was correct or not, because it's a 0-1 prediction. You have it or you don't have it. But there are many other loss functions to include or to kind of use in your neural network. One reason that we didn't focus on this too much is because it's not really an optimization strategy, because theoretically there's going to be one loss functions, sometimes more than one, that you know are more applicable to the project that you're doing. But it's also very easy with Keras to kind of change this. You could change it to something like mean squared error, and it's going to do the same thing, except it might not be ideal for this example to use the mean squared error loss, but there's a lot of losses to consider. And so that's why over here at the end, we have set up a little neural network playground for you where you can kind of set your optimizer, set your loss function, and this could take you to a link where it kind of shows you all the options you have. So these are kind of different loss functions that you could have just by including them in little quotations, or the same thing with optimizers. So we tried SGD, and Atom, but there's other ones as well that you can definitely look into. And yeah, so you can set that. You could set a batch number and epoch number. And after you set things up here, you can just run this entire neural network. So we've created a new one for you where you have here your batch, which you've set at the top, your epoch, which you set at the top, and over here your optimizer, which you've set at the top, and your loss function, which you've set at the top. And then play around with it and see how it impacts your accuracy, how does it impact your epoch loss, things like that. And I think it's going to be really useful to just go through this on your own and try completely absurd values just to know how it works. And all you have to choose, or all you have to do is change these 4 lines. I'm glad you think it's useful. Yes. So yeah, that's just kind of to conclude it. And that's why I said that last little thing about losses, because it might be nice to try out some losses here. But that essentially brings our workshop to a close. One other thing you could do actually before I conclude, because I said I would talk about it, is you could add more layers. So if we scroll to the top, when we first created this, over here when you say model.add, we had one hidden layer. If you were to add, like, I don't know, that's not what I wanted to do. You could add one here, and then see how that impacts it if you have more layers. And if you do add more layers, then maybe it'll become better. Maybe it'll become worse. Chances are it won't be worse. But it's something to try out just for yourself. And usually adding layers is going to be useful, but it might add computation time. And so it's a trade-off, right? Accuracy and computation time, loss and also accuracy. And you really want to try out what works best for your data set. Now, that officially brings our workshop to a close. So what have we learned today? We learned how to play around with different hyperparameters like epoch sizes, like batch sizes, and learning rates. And we learned how to implement a regularizer through either the kernel regularizer in Keras or by adding dropout layers in our neural network. And we saw how all of those things impact our accuracy and our loss in our network. And so hopefully you leave this workshop knowing a little bit more about how to optimize your network and how to play around with values. And hopefully you get a better sense of why it really does matter to sit down and experiment with different values to see what works best. So that is all. Does anyone have any final questions? Why should you take a data scientist with you into the jungle? They know how to take care of Python problems. That is a perfect end to this workshop. I think I have to stop recording just so that there's that ending. Perfect. Okay.